Okay, any question? All right, so the idea of the Kirchhoff circuit rules, because generally I think you have a good idea about now the Ohm's laws, or Ohm's law, right? Ohm's law mean if I have a resistor and then which is connected to, let's say, a battery and the switch and then so on, then when the current passing through the resistor, voltage across the resistor should be equal to the current time resistance itself, right? Now, this is fine to use for one single item, but if you have many resistors and many voltage supply across a circuit, then the Ohm's law itself not going to be enough to solve that circuit problem, like this one, for example. Figure number one, I have two batteries and then three resistance, and then three resistance are completely different way connection. I can't really simplify them into equivalent resistance at all. So we need something beyond the Ohm's law. Okay, that's the idea of Kirchhoff circuit rules. So there's two Kirchhoff circuit rules. One is called the junction rule. Junction rule is a very simple idea. So the junction rule, it's like the continuity rule, which means if something comes in, that should go through the path, right? For example, let's say if I have a T junction, let's say this is point A, and then there are three lines are connected here at point A. If something coming into the point A, let's say this is current I in, and then at point A that going to be divided into I1, and then this direction is going to be divided into I2. So we can simply say I in should be equal to the I1 plus I2, right? So that's the idea of junction rule. Technically, whatever comes in should goes away, right? So that's very simple idea, like the water connector, okay? So anything new there. So that equally valid for the current too, or water connection or any other flow. But the circuit loop rule, the Kirchhoff loop rule, is actually the important one. So the loop rule is actually talking about the voltage given to the circuit and the voltage drop across the circuit. Okay, so the idea of loop rule is this. Let's say, for example, I have one battery and then which is connected to a resistor, and then let's consider only one resistor situation. Okay, first, to understand the situation. Now this is a battery, this is voltage supply, this is a resistor, so the voltage going to be drop across that. Okay, negative, positive. Let's consider this point is A, this point is B, this point C, this point D. Now if I start from point A and then if I starting to move through this loop, right, so that we call the loop direction. Okay, I'm going to start from A, going to go to B, then B to C, and then C to D, and then going to come back to A. Okay, that we generally call the loop direction. You can pick where to start, doesn't matter. I'm going to start at A, then going to go to B, C, D, back to A. Okay, so I have to come back where I started. Then we generally call, we have a closed loop. Okay, now if I'm moving through that, what I'm going to do, we're going to take a look how the voltage actually adding and dropping across this path. Okay, so let's consider this is the path direction, and then this is the voltage. Now I'm starting at A. Point A is directly connected to this point right here, 0. So which means that point A voltage is 0. There's no volt at all. Then I'm going from A to B. This side is positive, so the voltage increases rapidly into some maximum value. That is the battery voltage E. And then B to C, it's a wire. There's no voltage drop. It's going to remaining as it is. Then when you go from C to D, you can see I'm passing through a resistor. This side is connected to positive, other side is connected to negative. D is technically connected to negative. So this one is actually directly dropped back to 0 because point D is actually connected to A is connected back to 0, right? So that's the idea. Now this is voltage adding, that voltage adding to the system, that is the battery voltage. If you go from battery from negative side to positive side in a loop, so you're going to get this voltage increment. If you go from resistor from positive side to negative side relative to the battery connectors, then you're going to get huge voltage drop. That's the idea of the circuit loop rule technically. What it tells you, if I go through a loop, if you select a loop and then go through a loop and then take a look, all this sign is sum, okay? Summing, adding everything. So if you sum up all the battery voltages and then if you add all the current and resistance values, which mean the voltage across resistances, that addition should give at the end zero. That's the idea, okay? Because one is voltage adding up, one is voltage dropping. So look like positive and the negative numbers adding together, you must get zero. Okay, that's the idea of the loop rule. That's the important one because here we take a look that for one loop, but this can apply for many number of loops in the circuit. For example, like this circuit right here, or maybe even complicated circuit like this one, okay? And even more complicated, like we can have more loops, like even more than 3, 4, 5 loops, and then a different number of resistances, voltage supplies, and then so on. Doesn't matter how many batteries or resistors are there, still we can apply. If we have identify a particular loop to progress through, then that law can be applied, okay? That's the idea. So we gonna testing out these two. We are testing out this guy, junction rule, and the loop rule. Any question? Okay, there's a one more thing. Junction rule is fine. It's very simple. It's like a continuity equation. But when it comes to the loop rule, depending on the current direction, you can see now this circuit has a current emitting from positive direction to negative direction, right? Depending on current direction and the loop direction, loop rule come with the sign rule. So we have to put them together. If not, loop rule itself not going to valid. Because like, for example, instead of starting A to B, I can start A and then go this one direction, right? Because loop direction is the person's choice. It's not really anything like uh, like a the very precise rule to say like start from here and then go to there. That rule is not like that. You can start any place on the loop and then you can move any direction as you wish. Because of that particular scenario, loop rule come with the sign rule. That's very important. If those two not going together, then we not doing the right thing, right calculation. So the sign rules are actually summarized right here on your page number 2 lab manual, okay? If I have a battery, if I go from battery direction positive to negative side, this blue line is the loop rule, okay? Loop direction, okay? Where are you moving? If I move from positive to negative, then the battery voltage come with the negative sign because I'm moving from high potential to low potential, okay? Finally is lower. Because of that, I have to use negative sign for the battery voltage. But if I go as I did earlier in my example, negative to positive direction, battery voltage is just positive, okay? And if I go in the resistor, you have to take a look two things. Blue line is the loop direction, that where we are moving from one end to another, and the red arrow is the current direction, okay? If both are same, resistor voltage is negative because you go from positive side to negative side. Finally is lower voltage, okay? So that come with the negative. But if you go opposite direction to the current, you going from negative lower voltage to the positive voltage higher, which is the higher voltage is the final, then this is actually positive because the voltage difference is always final minus the initial, right? That's the idea. So in this case, you're going to get 0 minus large number. So the earlier case, 0 minus large number, but this case, positive minus 0. So you're going to get the positive number. That's the most important thing. So if we have to follow very carefully the sign rules when we writing down this formula. We can't just write it. I have to follow exactly sign rules attached to that, okay? Which mean if I do that for this example, let's do that for this particular example right here. If I do it for here, If I start from A, let me draw that again. Just one resistor, okay, nothing much. One resistor, one battery, and then one switch. R, negative, positive. Current go from positive to negative, right? This is point A, point B, point C, point D. Let's select the loop A, B, C, D back to A. Let's apply sum of all the E plus sum of all the I and R is equal 0. Only one voltage. I am moving from A to B, negative to positive, positive E. And then I have only one resistor, current I. This is the loop direction, C to D. Current direction and the loop direction are same. So I have to use here minus times IR. Then you can see, since I have one resistor, I'm ending up look like I apply a Ohm's law to this resistor, right? Voltage across the resistor should be equal to I and R if you bring this to the other side. So that actually validate that rules, okay, that sign rules automatically. This is for one resistor, but the experiment we're going to do actually multi-resistor, multi-loop circuit. That's the plan. It's a very simple experiment. We just validating these two laws, circuit rules. Okay, any question? All right, then let's continue. You can click the simulator link. I think that should be on page number 3, right here on the middle part. It's the same simulator. We use this now many times. I think everybody familiar this now. Just double click on the lab option. There's two options on that simulator. Okay, use the lab option. Okay, now let's build the circuit first, right? So we are trying to analyze this circuit right here. So there's 5 resistances, 2 voltage supply. Okay, that's the one we're analyzing. So we need to build this circuit first. Okay, let's build that first. I need 5 resistances, 2 voltage supply here. Let's build that first. We can change the resistor values later. Okay, let's build it first. I need resistor here, and then another resistor here and here, another resistor in the middle. Values we can edit in a bit. Okay, another resistor in the middle, and we'll keep a little bit of space between these. We can connect wires in a bit. And then I need 2 batteries, one battery here, positive side to the down. Let's take a look, the positive side to the down, this green side, and the orange side, positive side to the up. Okay, change another battery on the other side, positive side to the up. Now let's connect with the wires. 1, 2, 3, fourth one here, and then connect all of them with the wires. We could connect directly resistor to resistor. Don't do that because we may need ammeters to measure current and then so on. It's better to have wires in between the resistors. Okay, then we can disconnect them, measure the current and then so on as we need. Now let's change the values. Okay, let's take a look the numbers. So what resistor R1 and R2 and R3 and then so on, and the voltages. Voltage E1, E2, 45 and 30, right? So let's rechange battery 1. Click on the battery, then change the voltage of the battery. You will see the battery around it highlighted with yellow color, and then the slider appear on the bottom right. You can change the number into 45, 45, 45, and then that is E1, E2 is about 30. So the other side, D2 is the far right side battery, right? So that should be 30. And then let's check the change the resistances. Okay, R1 is started green color, this bottom, and then R2 bottom loop orange, R3 bottom top orange loop, R4 green orange loop top, then the purple one in the middle R5. Okay, so let's change those values. R1 18, R2 47, 27, 33 and 12, right? R1 18, click on the resistor 1, left hand side bottom R1 18, and then next one 47, this one is 18, R2 bottom right loop 47, 47, 47, and then R3 which is 33, right top resistor, 27 right top resistor, that's the R3 which is 27, and then R4 which is on the left top resistor which is 33, this one left top resistor which is 33, and then in the middle one which is connecting the both loops which is the R5 which is 12. Okay, just 12 ohms. Make sure those values, best way to do that is click on the values right hand side very top, you will see the values. Okay, click on that, then all the numbers will show up, and also click on the conventional current, that it will show up red arrows, because that important. Electron direction is opposite to the current, we don't care that, but the current direction itself important. Reason, when we moving through the circuit, we need to apply the loop rule. Each time when you apply the loop rule, you have to apply the sign rules accordingly. So the sign rules depending on the current direction. So that's why show up the current direction by clicking the conventional current red arrows. That will be useful. Okay, all the values are visible, all the current direction are visible, circuit working fine. Anybody have any problem with the circuit?
My arrows look like they're going the opposite way.
Then you need to take a look, numbers or something definitely not right. Check all the numbers, all the resistor values.
It's exactly the same.
Then take a look the battery directions.
Oh, yeah. Okay. I think that's it.
Okay, and also you can check the circuit diagram right here. You can see the battery sign and the circuit sign. If you click that circuit sign, you can really see the circuit diagram, right? That exactly should look like this circuit. Okay.
Okay.
All right. So any other question? Let's take a circuit picture right here. We just need one of them. Um, let's add that into here. Insert illustration. I'm going to use the screen clipping inside this Excel. I'm going to take the whole picture of this one, including all the options and everything. Okay. Generally that gonna go into procedure section, but since you're not doing lab report for this one, we don't need that picture much, but we'll leave it here. Okay, this area somewhere here. Okay, and that will be our only figure for today's experiment. Okay, it's gonna be figure 1. We can just say figure 1, we can say the circuit simulator, or that should be fine, I think. Circuit simulator. Okay, then let's take a look now. The step number 1, we'll record all the values because we need that precise numbers. Okay, so this first table right here, we'll record the given values: C1 45, E2 30, R1 18, R2 47, R3 27, R4 33, R5 12. Okay, And we should not record more than one decimal place because the accuracy on your simulator is up to one decimal place. If you see more decimal places on your Excel, you know you can edit that always. Highlight that area where you want to edit the decimal places. Then home menu bar. In the middle, you see the numbers and then you see left and right arrows. Click the right arrow once or twice. Then you will see the number of decimal places can decrease accordingly. Okay. We should record only whatever we read directly, not more than that. And in terms of accuracy point of view, otherwise has no meaning. Okay, any question? Okay, then let's take a look. First table. So investigation of junction rule. Now to investigate the junction rule, what I need is to measure the current, right? So let's measure current I1, I2, I3 according to our diagram. Let's say I1 come in here, this red one via R1. I2 is the current passing through right here via R2. And then I3 in this junction C, what is going up, okay? So let's measure those two. Now, if I want to measure current values, ammeter must go serially to the circuit, right? I have to break the circuit and then put the ammeter in. So let's bring the ammeter and then let's break the connection from the R1. If you click on the connection point, the scissor will appear. Just click on the scissor, it will break. Then you connect that break point via the ammeter. Then you will see current value. That's the number we interested, right? 0.80 amount of current passing through this resistor. That's the green part on your circuit right here. So we'll consider that part, that whole green part has the same current, okay? Because it's same line. There's no under junctions. So that current comes into junction C, okay? So I1, let's say 0.80. And we measured that in terms of unit amps. Then let's measure I2. You can actually break this and then bring it to the other side, or you can leave it like that because you can actually add more ammeters as you wish. It's a simulator, doesn't matter. You can break the right side loop from here and then we'll add a new ammeter there, right? So we have more freedom of doing this than the in-person setting, right? We can bring more ammeters. And the current passing through now right side, this whole part, that's the orange part on the circuit diagram, that is about 0.46 amps. Okay, let's record that I2 about 0.6 amps. Now I need to measure current passing through middle right here through this resistor. Okay, now I need to break somewhere here and then connect that part by using another ammeter. You need to rearrange the shape, okay, otherwise circuit looks ugly. So make sure it's nice symmetric shape. Let's connect this part here, okay, and then let's connect this part to the top little bit. All right, now that's the current passing through this resistor, right? About 0.34. That should be then I3, 0.34. Okay, now if we're doing this in-person setting, we don't have that much freedom to, connect three ammeters. We have only one ammeter per group. So what we're going to do, break one connector at a time, measure it, reconnect it, go to the other place, and then break it, connect the ammeter, measure the current, and then go on like that. Okay, but this is fine. It's a simulator. We'll add many ammeters as we wish. Any question? Okay, then now to test it out, this is the junction C on your circuit right here, right? So whatever comes in, only the red arrow comes in. purple arrow and the orange arrow goes out, then which mean if I add purple and orange arrows, that number should be equal to the red arrow, right? That's the coming in. So let's check it out. So the current coming in is actually only I1. So that is about 0.8. Current going out is actually the addition of equal sign, addition of I2 plus I3. So we're getting exactly the same. That's the idea of junction rule. Okay, junction rule mean whatever come in should go out. It should be continuous. Okay, so we get exactly what we expected. So we have exactly the same answers. So let me add that equation right here. This is going to be then I out. Okay, I in actually just the current I1. Okay, I in is equal just current I1. That's the two functions we need for this table. Any question? Percentage different, there's no even meaning doing it, right? It's the same numbers, right? Why bothering? We just put 0 there. We could write an equation, but what is the meaning? It's just same two numbers, right? So what is the meaning comparing to same two numbers? You're going to get 0 anyway. We just put 0 there, okay? If you do an in-person class, depending on the accuracy of the measurement, we might see some percentage difference between these two. But this is a simulated result, we're getting perfect answer. Okay, guys, any question? All right, then let's continue. Now let's go into loop rule, right? Now let's write it down. Loop rule 3 equation. Technically, you should calculate these three current values by using the tree equation. Okay, so that calculation I will let you to try. But in experiment we do all the measured values directly. Okay, but I will write it down. Those three equation may be useful for your lecture classwork too. You might get the problems similar to these ones. Okay, now let's apply the loop rule for these two loops, left and right direction, small two loops, loop 1 and loop 2. And then let's apply the junction rule for C. I have three variables in algebra. You know, if I have a three variable, I need three equation to solve that, right? Let's take a look how to get those three equations. So let's apply loop rule for loop number 1. If I apply for loop number 1, we'll start, usually it's better to start negative side of the loop, negative side of the battery in the loop, and then continue. Okay, that's the easiest way, but technically doesn't matter. You can start any point on the loop, come back to the same. As far as it is a closed loop, you're fine. Okay, so we'll start loop 1 from, I will add where we going right here. We're going to start from A, we'll go to B, we'll go to C, then we'll go to G, we'll come back to A, right? That's our loop. So what loop rule says is sum of all the potentials given should be equal to the sum of all the potential drop through the loop. Sum of the potential given here is actually only this battery, E1, right? Which is about 45 volt. That positive because I go from negative side of the battery to positive, okay, A to B. Then let's take a look the sum of all the voltage drop across resistances. If I go from B to C, loop direction is same as the current, this green arrow. Current passing through here is I1 multiplied by R1 times R1, and then that number should be negative. Reason, the loop direction and current direction is same, right? That's the idea. So that's the sign rule. Okay, those two has to go together. If not, we're doing something wrong. So that's really important because otherwise loop rule not going to work. Now if you go from C to G, purple color part, Current direction is the purple arrow. Loop direction is the C to G, where we moving on that line. Both are same, negative sign. Current passing through is I3 multiplied by R5. Okay, we can put the numbers actually if you want to, but let's put without numbers like the variable first. Okay, and if I pass through G to A, current direction and the loop direction same, so I should get minus sign. Current passing through that green part is I1 multiplied by R4, and everything must be equal to 0. That's the idea of loop 4, right? We know all the numbers except I1, I2, I3. Then we can put the numbers except I1, I2, I3. 45 minus R1 is about 18. 18 times I1 minus R5 is about 12. 12 times I3 minus R4 is about 33 times I1 again equals 6.
Professor,
What's up?
I'm sorry, I have a stupid question. How did you get the two rows in the one?
Oh, that's what you have to do now. Let's say I want to, let's say if I click here on loop 2, if I want to get a new row in the same, if you are in the Windows machine, you have to do click Alt button and then hit enter together. If you are on the Mac machine, I think the Alt button should be Option button, Option and enter in
Ah,
the Mac machines. Okay.
okay, so Alt and Enter.
Hmm.
Okay, all right, thank you.
Yeah. That will automatically extend the size of the that cell. All right, so that's the idea. Now you can see I have three variables, so I need to have a three equation. If I build two more, then I may be able to solve them and then figure out the I1, I2, I3. But we're not going to do it here. We just write it down to see how that formula look like. That's it. Okay. And everything else right here we do by using measurement. Okay. Rest of the three tables. Just write it down for loop 2 also to get to see how it look like. Any question? Okay, if I do loop 2, that is this right hand side loop, right? Similar to last one, let's start at D, negative side of the battery 2. Then let's continue through that loop. Okay, if I start at the battery E2, which is 30. If I go from F to G, loop direction F to G same as the current inside that R3, there should be negative sign. R3 is about 27, current passing through that is I2. Then if I go from G to C, that where the difference, okay, G to C, direction of the loop is opposite to the purple arrow. That's the current. So which means that should come with the positive sign. So the R5 is 12, current passing through is I3. Then if I go from C to D, current and the loop are same, negative sign, R2 is 47 times I of 2, everything equals 0. That's our equation 2. And then we can build another equation very easily by using the junction rule also. I will add that also here somewhere outside this table. Because instead of loop rules adding 3 times, I can just use the junction rule. I in should be equal to I out, right? If I do that, I in is I1, current come in, should be equal to I2 plus I3. That's another equation actually. We can build 4 equation if I want to, okay? Because we can do this for outer loop also. Let's write it down the outer loop too. Outer loop, let's start at point A, B, C, D, F, G, back to A, okay? That's the outer loop without passing through this middle part, okay? If I start at A, I have 45 voltage here. Then I have 30 voltage here, 45 plus 30, 75 voltage in total, okay? That's the sum of all the voltages. Then you start back again at here, then collect all the I and R's. B to C, current and loop direction same, negative sign. R1 is 18 times I1. C to D, current and loop direction same, R2 is 47 times I2. D to E is the voltage, we already added that one. F to G, current and loop direction same, R3 is 27 times I2. Then G to A, current and loop same, negative, R4 which is 33 times I1 which is equals 0. Forgot the sign here. This is also negative. This is also negative. Then we can simplify this and then solve, for example, these three equations simultaneously by using the algebra to figure out what is the I1, I2, and I3. Okay, I don't know how much the level of the correction you do in your lecture class. Sometime I don't think it gonna ask three variables at the same time in your question. It might, okay, I don't know. If it asking, you may need to really get to use this kind of work, okay. That extra part you can get an idea how to build those equations, okay. Okay, any question?
Yes. Do you want us to label the loop 2 and the outer loop like you did for loop 1?
Yeah, we can do that actually. Yeah, that's loop 2 is we started at D, right? D, F, G, C back to D, and then outer loop we started A, B, C, D, F, G back to A. So that's not visible. Let me increase this a little bit. Okay. All right. So that's better to add that actually. Whenever we using the loop rule, we really need to uh, tell what the direction of loop is. That's extremely important because that sign rule depending on that. That's a very good point. We should really tell what the direction is. Otherwise, person who watch the reading that has no clue how we write this formula. Okay. Okay, guys. So any other question? Then let's investigate the loop rule circuit, loop rule number 1, number 2 actually. Okay. So the loop rule will investigate for loop number 1 and then loop number 2. And finally, we will take a look the power dissipation and the power supply in each loop. Okay, that's the plan. So it's a simple calculation. So loop number 1, we'll measure the voltages across each resistor, okay, and each voltage, and then collect them here first, okay. V through AB, BC, CG, and GA, okay. That's loop number 1. So we're going to start. We need a voltmeter, and then we're going to start negative side of the battery to the positive side of the battery. 45. So there's no difference at all. E1 is 45 and the voltage measured unit should be volt. Okay. Now when you're moving through the circuit, when you measuring the voltages, remember this is extremely important. You have to bring these probes very carefully relative to how you started with. Now this is the positive side of the battery, okay. That probe has to go this part of the resistor. Okay, front of the resistor relative to the motion of the current and the loop direction, okay, and then it followed by the negative side, negative probe. Then you will see voltage across that resistor is negative. That's the reason that sign rule is written that way, because if I really measure according to my loop direction, voltage across each resistance should be dropping. Okay. If I go against the current direction, this number will change into positive. You will see that when we measuring the voltage across our right hand side loop. Okay, that's the idea. So that's the measured voltage across resistor number 1, which is about minus 14.44. That negative sign is important. Okay, you have to report everything as we read it. Okay, guys, any question? All right, then let's measure same way. Okay, bring the red one first, go to the front of the next resistor, bring the black one followed by that. It goes to the back of the resistor, negative 4.10 across R5, negative 4.10. Then similarly, positive probe first, followed by the negative probe, and it is about negative 26.47, right? Minus 26.47. All right, any question?
So what,
Now,
just pure curiosity, what would happen if you place the negative first?
when we measuring the next loop, you will see that, because if we go against the current direction, you should see it as a positive number through the resistor. Okay, we're going to do it in a bit on the loop 2. Okay, any other question? Okay, so now we can check it out, all of these numbers, by calculating by using the Ohm's law for each of the resistor. If I apply the Ohm's law, for example, if I apply the Ohm's law for resistor 1, this guy, left hand side loop, bottom right here 18, I know the current passing through dot 80. I know the resistance value. If I apply the Ohm's law, voltage drop across this resistance should give me the same answer as I measured, right? So I can actually calculate those numbers by using the resistor and the current passing through that. Okay, that's what this column is. There's no calculated value for battery, right? So we don't need to put anything here. We can't calculate battery voltage at all. Battery voltage can be directly measured. Okay, 45. You can put this 45 there, that's okay. But all the voltages calculated values through resistor, we're going to use current and R by using Ohm's law. Now current I1 is, we already measured 0.8. You can also see here 0.8. And the resistance R1 is 18, equal sign, current is 0.8 multiplied by resistance is 18. However, if I use the sign rule correctly, my loop direction B to C same as the current direction, that voltage must be negative, right? I should add that negative sign according to the sign rule. So you may need to multiply this by negative sign also. Multiply by just negative 1. Then you should get about the same number. You see there's a rounding error to the last decimal place, but it almost perfect. Okay, that's the idea. So the Ohm's law is still valid. It's still valid if you apply the Ohm's law per given item in the circuit. I can't apply Ohm's law any more than one item in the circuit. Okay, because circuit itself now too complicated, it has too many items. That's the idea. So any question? Okay, then let's continue and then do those calculations for next resistor R3, I3, R5. That also we know according to the sign rule, loop direction and current direction same. I should multiply by negative 1 to get the negative sign. I3 is about 0.34 and then R5 is about 12. Multiply by 0.34 multiply by 12, we're getting about the same number. Okay, there's a very small difference, that just the rounding error, otherwise it's about the same answer. And we'll do the same for R4, equal sign, according to the sine rules, it should be negative. Multiply by current I1 again 0.8, multiply by resistor R3, about the same. Okay, so that confirm is still Ohm's law valid per given item in the circuit. Okay, then PD, there's no units PD. You can just put percentage sign there. For the battery voltage, even not meaningful actually comparing it. We can just put 0 there, but these three,
Wait, can
yeah.
you go back
Yeah.
to
To
You
what?
went a little too fast.
the I1 R4?
Oh, sure. I1 R4.
The calculated part? How
This
did you
one
get
right
that?
here.
Okay.
0.8 times 33.
And also the one above it.
That should be 0.34 times 12 times -1.
Okay, and also the 45. How did you get that?
Which one?
The 45.
45 we can't really
Just the
calculate.
45.
That's a 45. It's a battery, right? So
Okay.
battery voltage we can't calculate.
Okay, thank you.
Yeah. Okay, guys. Any other question? Okay, then we can compare these, right? Comparison is simple. You just need to do percentage different, right? ABS, open brackets, different between these two numbers, D33 minus E33, divide by open double brackets, D33 plus E33, and then divide by 2 close bracket, multiply by 100. Let me copy paste that equation down here. The PD always must be a positive number.
Can you paste that formula in the chat, please?
Yeah, we'll do that. We should do actually ABS just very outside right here. There should be, we'll put another parenthesis, okay, because ABS must be always a positive number. I want to get rid of that. Let's do one more parenthesis here and then one more parenthesis here. Okay, because when you do percentage error or percentage difference, that must be always a positive number. Okay, so let's put that here. Okay. All right, any other question? Negative, this guy, negative 14, 0. 0.8 times 18. Copy paste those equation also. We can copy all of those into here actually. Okay. All right, any other question? Let us copy all of those into these places, then you can see it clearly. Okay, that for that one, and then this one also, let's copy paste into here. Okay, now this one you can click and drag, right? Then it will complete the rest of the calculation, and then that function I will add just under this table somewhere here. That's the PD equation. That's only different equation. I also add that into the chat box. Okay. All right, so let's take a look now. Sum of all the voltages given should be equal to the sum of all the voltage drop, right? If you add all of them together, we should get 0, right? So let's do it here. Let's do sum of all the E's, which mean only 45, right? Just 45 there. Sum of the battery voltages measured. Sum of the battery voltage calculators, 45 again. Sum of all the voltage from the voltage drop from the Ohm's law, I need to add all of these three together. Okay, let's add them together. Equal sign, adding this number D33, voltage across R1, voltage across R5, voltage across R4. So we're getting about the same number. That's the idea. If we add all the voltage drop, that must be a negative number. And then voltage given is a positive number. Adding these two, we should get 0. So we can add these two together, voltage given and voltage drop. We're getting about little bit of error, that's just a rounding error. Otherwise, it's about the same. Okay, this guy right here, adding all the voltages together. Okay, any question? We can do the same for the calculated values too. Okay, we can do the same for calculated values. And let's add all the voltages together. E33 plus E34 plus E35. About the same. So we can add those two numbers together to check it out whether we get in the 0 or not. That's what we're checking here at the very last cell. So we expecting it to be 0, but we can get little bit of error depending on the rounding error and the calculation, depending on the calculated values. Okay, the rounding error actually come from the ammeters. Okay, guys, any question? That part we don't need to do PD at all. Okay, so this part right here, just leave it empty. So that no need to be doing anything there because we already compared earlier percentage differences. Okay, this part just leave it empty. Okay, any question? Okay, that the same thing technically that confirm the same thing we're going to repeat for the other loop on the right hand side on the next table, but that table confirm the idea of the loop rule and the sine rule and also the Ohm's law. Okay, so those are the objectives technically for that part. It's not just single calculation, it actually can give us a lot of extra information. Any question? Anybody have trouble on doing any of this calculation? Good. Okay, then let's take a look the next loop. I mean, nothing new then. It's the same thing we're going to repeat for actually loop, a small loop on the right hand side. Okay, that's the plan. So we'll repeat the same exact calculation, but for this small loop on your right hand side. Okay. Ask if you have any question. Okay, from the previous table. Let's do the same thing then. We can measure directly voltage by using volt. We can calculate each voltage drop across resistances by using Ohm's law. Right, I and R's. Then we can compare them to check it out. The Ohm's law first, the first part here. Then actually last part we actually comparing sum of all the voltages. Okay, this part again on this table we're going to leave it empty because nothing much to do there. Okay, it's the same exact table like the previous but for loop 2. Let's take a look what are the voltages given is only the battery number 2 in your right hand side corner. That's a 30 volt, right? So there's no calculated value for battery. Okay, that's going to be same given value. And now let's measure, right? So let's bring the voltmeter. Then let's measure starting from the battery negative side to the positive side. So we get in 30.00, right? That's good. Then let's measure next resistor, right? Positive probe first, followed by the negative probe, okay? Now you can see the current direction and loop direction same. That should be negative 12.44. Minus 12.44. Okay. Now follow carefully, okay? First, red probe goes to the bottom end of the resistor 5. Then follow the negative or the black probe. You can see if I set it up that way, voltage across R5 now showing you positive number. Reason, if I'm moving from top to bottom on that middle segment, then I'm moving actually against the current direction. So I'm going towards the higher potential side. My final potential is higher. Potential difference, usually we write final minus the initial. So I should get a positive number for that. Okay, that's the idea. Those are actually the reason why sign rules are written in a certain way to match with those conditions. Okay. Now this number earlier, if you remember, we measured that earlier too. Earlier it was actually true R5, which is actually a positive number, right? I3 R5. But now earlier it was a negative number. Now it's a positive number, 4.10. Exact same number. There's no difference at all. Middle segment is common for both loops. Okay, question. Then that's it. Then we'll followed by the path. We'll measure the voltage across next resistor on our right hand loop, negative 2166 minus 21.66. We can calculate all of those like we done earlier by using a Ohm's law, right? I2 R3, I2 passing through here is this number 0.46. That's a negative number, equal minus 1 multiplied by 0.46 multiplied by R2. This should be I2 R2 F to G. Wait a minute. Did I miss something here? Oh, I know what happened. So we started here, right? Battery negative side, then go upward direction. That's why we'll start from the F to G. Okay, this part. Okay, so let's do that. So the current and path direction same, negative sign multiplied by I2 is same, 0.46 multiplied by resistor 327. So we're getting about the same. There's a rounding error on second decimal place. That's totally fine. Let's check it out. I3 R5, right? We are moving top to bottom, G to C against the current. Sign should be positive. Sign is positive. I3 number is 0.34. R5 number is 12. 0.34 times 12. About the same. We calculated that earlier also. Then the last one here, equal sign, current and path direction same, minus sign, multiplied by the current is 0.46. Resistance there are 2, which is about 47. About the same number, okay? All right, guys, let me add those also functions if you want to check it out on here. Okay, all of those on column C are those calculated functions. Okay, you can check it out the equation in case if you want to check that. All right, any question?
Yes, we don't have to add the formulas, do we?
No. These formulas you don't need, because since we're not writing the lab report for this one, you don't need that ones. If you write in the lab report, I usually put it all those equation under the table, right? Because that has to go to your report, but this one is fine. Okay, any other question? All right, then let's take a look. Percentage different as we done earlier, comparing calculated and measured value. equal sign, ABA's double brackets open, difference between these two numbers, divide by parentheses, double bracket, addition between these two numbers, D43 plus E43, divide by 2, close brackets, close another brackets, multiply by 100. Okay. So that's the same command we used earlier. Let me copy paste that into somewhere here. PD. And also let's add
Can you
that
paste that in the chat box, please?
here. Okay, should be on the chat box now. All right, so any other question? That one you can click and drag, right? So that's doing the percentage different comparison between voltage measured by using the Ohm's law per each resistor and the voltage calculated for each resistor, okay? And the voltage of the battery, we can't do anything. We can't calculate that. That's a given or the measured value only. Then let's check the loop rule for this loop. So I need all the voltage given, that is a battery voltage 30. Calculated doesn't matter, battery voltage is only the given number, we can't do anything. But sum of all the voltage drop across resistances, we can do with the measured and the calculated separately, okay? Adding again these three numbers, D43, 44, and then 45 together. Those are the voltage drop across all three resistances. You can see these two numbers are exactly the same, one positive, one negative. That confirm our voltage loop rule is actually correct. That's the idea, okay? So I'm just adding all the voltages together to get this. Let me add that also maybe here. And same for the other one. We can add E43 plus C44 plus C45. All the voltage drops together about the same. It's not exactly 30, but it's close enough, okay? And then let's compare those two numbers by adding together, because if the loop rule correct, we should get 0, right? If I add voltage given from the battery plus voltage drop across resistances, we should get 0. This one, for measured values, it's worked very perfect. We're getting 0 there, but the calculated values, we're gonna get little bit of error due to rounding, okay? Equal, just add these two cells together to check it out. We're getting very small amount of error, but that's totally fine. It's just a rounding. Okay, questions? All right, guys. So we almost done. We just need to do one quick check about the power of the circuits, each loop, and then we done from that. I think, yeah, that's the last table. Any question? All right, then let's take a look the power. Idea of the power, I think you came across in your lecture class by now. So the power means the voltage times the current. And also the power means how faster energy is actually supplying or energy disappearing, right? So now you know the Ohm's law is V equal IR. If I combine these two together, I can write the power differently, right? So power can be either VI Or I can get rid of V by using this. It's going to be I square R. Or I can get rid of I by using I equal V over R. Then it's going to be V square over R, right? Yeah. So we can do actually differently depending on what we need to calculate. For example, if I have a battery in the circuit, if battery has a certain current passing through, let's say the battery voltage is V1, current passing through I1. So the battery does supply the energy, right? So if I want to find the power supply by the battery, I must use VI. There's no other option for the battery because we interested power supply there. But if I have a resistor on the other hand on a circuit, let's say R1 have a current passing through I1. Now that is power dissipation. Power dissipation means what resistor does, it's getting rid of or convert the power into a different type, or sometimes heating and then so on. So which means I have a freedom of doing that power any way I like. So I can use power for R1 by using I square R1, or I can use V1 square divided by R, or even I can use V1 times I1. So you can actually use any way, doesn't matter. All of these gonna give you the same number. But for our circuit, since we know the current and resistances, power dissipation is easy to do calculate by using those two. Okay. That's the idea. So the power in terms of general idea, so the power is the rate of change of energy, delta E over delta T. So in case I'm going to use here energy sign U because battery also we using E. So if I want to find the energy, if I calculate energy power times the time, then I can get the energy, okay? So the power unit is going to be joule per second. So that joule per second we generally use actually watt, okay? W-A-T-T watt, just the W sign. That's the idea of the power and then how we're going to calculate that. Any question? Okay, then let's do that calculation. So the power applied for loop 1, we know the unit going to be watt, that is joule per second, and power dissipation by using I square R, okay? Let me check that. For the power, same unit, okay? Watt equal joule per second. Yeah, this equation right here. So this should be I square R. That you need to correct it, okay? It should be I square R. I square, let's do times R. Power, we can just say voltage times the current. Given and power dissipation, we do I square R. Then we'll check it out, the comparison between those two, percentage different again. Let's do that for loop number 1. So if I go to loop number 1, only one voltage, current passing through is the red arrow, the green arrow, right? That green arrow is the I1. I1 we know number 0.80, voltage is 45. So the loop number 1 voltage supplied or the power supplied is equal, voltage is 45 multiplied by current is 0.80. Okay. So that's the amount of power, amount of energy giving to that circuit every single second, right? So that's the power supply. Let me copy that function maybe somewhere here on the top. That might be easier to see then, okay? All right. And let's do the power dissipation on the same loop, okay? Equal sign, parentheses, I need to do I square R for each resistances, okay? Resistor number 1, I is 0.8, 0.8 power 2 times the R is 18. Close bracket plus parentheses I square R for resistance in the mid part, that is the resistance 5. Current is 0.34 power 2 multiplied by R is 12. Close bracket plus open brackets. Top resistor on the left hand side loop, current is again 0.8 power 2 times the resistor is 33. Close brackets, hit enter. These two numbers should be about the same, but I'm getting slight difference, not exactly the same. So that might be most of the time the rounding error of the current values. Because the current is getting to the power 2, if I have a 1 decimal place error, that's going to give us a little bit of error there, okay? That's fine, I think. Any question? Let me copy paste that function also into, since that is a longer function, I'm going to leave it here, okay? Just under the table. This is the power dissipation for loop 1. Okay. Question. Then let's compare that percentage difference. ABS, open brackets, power supplied by the voltages minus the power dissipation divided by open brackets, power supplied plus power dissipation, D56, close bracket divided by 2 multiplied by 100.
Please post that in the chat.
Yeah. Okay guys, so let's do the same calculation for the right hand side loop, then we done from that. That's the last calculation, okay? Okay, so the right hand loop again, there's only one battery. The current passing through that is this number right here on the very right hand side loop, which is the orange line right here, right? That's the I2, which is about 0.46. So which means the power supply should be equal sign voltage 30 times current 0.46. Power supply on the right hand side loop is much smaller compared to the other one. Let me copy paste that also into the top of that cell. And let's do the power dissipation same way. I have to add 3 resistances I square R 3 times, okay? Like the previous function, equal sign parentheses. I for the top resistor on the right hand side is small loop is I2 0.46 to the power 2 times resistor 27 plus open brackets current passing through R 5.34 to the power 2 times 12 ohms plus open brackets current passing through very bottom resistor on the right hand side 0.46 power 2 multiplied by 47 and close brackets, hit enter. So there's a considerable difference actually in that than what we expected last one, I think. Okay, any question? All right, then let's compare the function.
Sorry,
Yeah,
I
what's
I
up?
just wanted to see the percent difference for loop 1, just the equation.
Which one? Cell D number 57?
Yes.
Okay, so let me do it here. P dissipation for loop number 2. Loop number 2 has actually huge error. That's okay. Okay, guys, any question? All right, so that's the last calculation we need. So I think we done all the calculation needed. Since there's no any lab report for this lab, just upload the data sheet, okay, before tomorrow midnight. And then that's it. If you have any question, stay on the call. Otherwise, we'll stop here. I will see you guys next week then.
Thank you, Professor. Have a good night.
Can you show the percent difference between the loop 1 and loop 2 at the very bottom? I just need the formula.
This one. Let's add this one also here. This is the PD equation.
That's in the chat.
Yeah, that should be also in the chat box. So this one for actually the cell number E56, okay? Then click and drag for the other one.
Professor, I just missed the first column for loop 2.
First column of loop 2.
Sorry, table 5, the power applied.
Oh,
should be
this one?
C57, yeah.
This one?
Yes, that's all I missed.
That is just 30 times 0.46.
Okay, thank you.
Professor, what did you name the picture that you took?
Picture we took just the circuit diagram actually in the beginning.
Just
right
call
here.
a circuit diagram?
Oh, yeah.
Okay.
You can just say circuit simulator.
Okay, thank you. Have a nice night.
Yep.
Professor, the percent error that you got for loop 2 was 21, correct? 21.04?
Yeah, that's right. Yeah.
Okay.